this is the next class for our MCQ solution. Do you guys have any specific problem that you would like me to ask me?
1.1 একটা প্রবলেম ছিল।
কত নাম্বার?
স্যার 1.1 এর 19।
1.1 and 19 চলে দেখি। What is the reasonable estimate for the average counting age of an athlete during a 100-meter race that takes 10 seconds? So for this case, once again, you have to assume the mass of the athlete, typical mass of the athlete. So you can guess what a regular grown-up person might weigh, something around 60 to 100 kgs. Here they have made the calculation with 80 kgs. That's why the numbers are all in this format. But you can take, if you take 80 kgs, but you don't have to take 80 kgs. I'm going to show you what happens if you don't take 80 kgs. You're going to get a number close to the correct answer, which you have to choose. Hold up, I'll be right back. If we take approximately the athlete's weight to be about, let's say, 80 kgs, in that case, we can get the exact number. So that would be half.
Sir, what are you talking about?
I'm talking about an MCQ question number 19 of 1.1. V would be about 100 by 10. This is average speed, which is 10 meter per second square, 10 meter per second. So that gives you 10 squared, which gives you exactly 4,000 joule. How about if you do not take this to be 80, if your assumption is, let's say, somewhere close but not exactly correct, let's say if you take it to be 60, you're still gonna get a number like this, half into 16 to 10 squared. That's gonna give you 3,000 joule. But if you have a look at all the possible answer choices that we are provided in this MCQ, we have 40 joule, 400 joule, 4,000 joule, 40,000 joule. So the only thing that they have, the number that they have kept constant is the value, the first digit of the answers. So they are all 4. The only thing that is different from all the answer choices is the number of zeros. So you can see this is a 2-digit number, 3-digit number, 4-digit number, and a 5-digit number. You can see that no matter what you choose for your mass, a reasonable choice of a regular athlete's mass, not mass, my bad. So if you take a reasonable estimate for a regular athlete's mass, in that case, you can get a number that is within the multiple of thousands. So that's that way. Your most logical correct answer should be C, not any other, that matches the range of the values that we have given, that we provided here. Does that make sense?
Yes, sir.
Good.
Sir, one. Sir, massের রেঞ্জটা মানে কতটুকু থেকে কতটুকু নেওয়া যাবে?
How much do you think a regular grown-up person, adult grown-up person weigh? How much do you think?
70, 80.
Yeah, you can take that as well. Still, your answer is going to be close to option choice C, not to any other else. Because they've given the distance is 100 meter and the distance and the time taken is 10 seconds. So the average speed is going to be 10 meter per second. So that's a fact. That's the number that we already get from the question. All that you are left to choose is the mass of the athlete. So whatever you choose, 70, maybe 70, then you're going to get 3,500 over here. But that will still be within the range, close proximity to option choice C.
Sir, 47.
বাকি কিছু একটা বলতেছিলা?
স্যার আমার 1.2 এর 13 এর কোশ্চেন ছিল।
আচ্ছা যাচ্ছে 1.2 দিচ্ছে। 47, what is the reasonable estimate for the diameter of an alpha particle? Okay, you are not supposed to know this from this chapter immediately. You should come to know about the physical diameter of an alpha particle in the relativity chapter. Which this information will be fed to you in this chapter. But for the timing, you are not supposed to know this. Diameter of an alpha particle basically means the diameter of a helium nucleus. It is the one of the very preliminary composite nucleus, 2 protons and 2 neutrons. I am not quite sure what this answer should be, but I think it's A is the option, I think 10 to the minus 15 meter. What is the correct option for this? Correct answer choice.
Sir, A.
A is the correct choice, so I guess right.
Yes, sir.
Sir, কোন question টা?
বুঝি নাই।
The কোন question টা?
47, 1.1 and 47, reasonable estimate for the diameter of an alpha particle. Let's not minimize this so that I can select and mark which one we're doing. Okay, 1.2 এ কোনটা বলছে তাকি?
Sir, 13.
13. Let's have a look. The density of the material of a coil of thin wire is to be found. Which set of instrument could be used to do this most accurately? Well, if you ask me, we are trying to find the density, so we're definitely gonna need the mass measurement. We're gonna need the volume measurement. So it's a coil of thin wire. So you have to understand it's a wire, it's a coil, which means you have enough length available of the specimen, and it's a wire mentioned to be wire, so the diameter is should be considered to be pretty small. So for small length measurements, micrometer screw gauge is the obvious choice, and for length measurement, because you have enough length available, it's in the form of a wire, you can go for a meter rule. And then to measure the mass, you need some digital balance, because you would like to measure the mass to a very large number of decimal places. That would be crucial for you to have a good number for the density, reliable value for the density. So have a look, which are the options do we have?
Sir,
Yeah, B seems like okay, bolo.
sir, top pan balance na like অনেক বড় range of weight এর জন্য থাকে?
No, top end balances can be designed to have a lot of different type of ranges, For example, the typical balance that we have in our laboratory, they have more fraction after the decimal places, so their actual highest value, highest means that they can measure is not typically more than 1 kilo. But however, if you consider the digital balance that the vegetable vendors তরকারি ওয়ালা এটা যেটা ইউজ করে ওটা টপ এন্ড ব্যালেন্স, সো ওইটা হচ্ছে ওটাতে একটা ডিফল্ট মাল্টিপ্লায়ার অপশন দেওয়া, সো you put the price of per kilo, it gives you the whole price by multiplication that can measure up to I think 15 or 20 kg. Then again, you can use top end balance for digital measurement as well. For example, the scale that is used to measure the total mass of the long trucks or 16-wheeler vehicles, container trucks to be more exact, they are also measured on the road while they stand on a top end balance. That's the digital scales. Top end balances can be designed to have a lot of different properties. If you go for a large range, you're going to lose on the precision side. You're going to have fewer values after the decimal places. If you choose a smaller upper limit, you can have more decimal places, but they can be designed to have a lot of different values.
Okay, sir. বুঝছি।
Beautiful. Do you guys know what a lever balance is like? Have you guys ever seen it or know what a lever balance looks like?
No, sir.
Sir,
You
ये পাল্লা?
No, lever balance, palla হচ্ছে beam balance. Normal, let me show you the differences so that you can have at least some idea that what these two different scales look like. Beam balance. Okay, this is beam balance. This is what I call beam balance. We have a beam on both sides. This is what we call a lever balance. So what is happening in a lever balance? I mean, that is, or am I wrong? Hold up. Yes, I was wrong apparently. Yeah, this is a lever balance. This is somewhat different. So before I should talk to you about the lever balance, I'll tell you a little bit about this scale. These are the scales which also uses the idea of pivot. This scale is gonna have a mass placed over here, and this is the pivot point. If I choose a slightly different image, maybe this would be easier for you to understand. This is the most common version that many laboratories might have had. This is the pivot point. So you can see there is a small side on the pivot side. So you can place the object over here. There is a certain scale that is calibrated to give you the exact mass of this thing. You have large mass over here, which can move pretty for balancing a very large mass. Then you can have a halfway small mass, which is on the third row. You can see over here, the behind picture. And then you can have a very precise small mass, which can move and give you fractions of a gram maybe, or maybe within gram, full integer values of gram. You can move this one. So the idea is that there are individual notches on this scale. You can have a look. There are some notches. The notches are not very visible for this image. If I could have a bit more clear image. Okay, I'll just take the first image and copy it, paste it, zoom it. Open image in new tab. Okay, can you see these notches over here? There is a notch over here, notch. All of these notches are here so that you can actually place the object in an exact known value. For so all of these large masses here, we can have 3 different masses. So you can see there is a very large mass. In front of that, there we have a pretty small mass. There is another small mass, and over here we have a very small mass. So this small thing is also a mass. Sorry, we have 3 masses over here. The last one is only measured for the fraction. The enter point, or do we have 4? I think 1, 2, 3. We have 4 masses over here for this single pan beam balance. This is also a beam balance because this is the beam on which the load is measured. The load is applied over here. So you have a weight-based unknown objects weight-based moment from on the left side, and that moment is perfectly balanced over here. This right side over here actually shows you whether you have balanced it perfectly or not. There is a mark over here and there is a 0 mark over here. Your aim is to place all of these masses on the right side in such a way you can have this arrow mark perfectly aligning with the 0, or at least as best as you can achieve it from here. So that way you can actually say whatever the reading over here, you can take all the readings, add up the values of all of these masses, and that gives you the total value of this thing. You can see over here it says that MB311, this model of this single pan beam balance, has a capacity of 311 gram with a precision of 0.01 gram. So it can measure up to 100th of a gram, which is really sensitive, and it can have a capacity of 300. So it's not that heavy loading of machinery, but it can measure very precisely. So that's another way to operate these devices.
Is digital balance more accurate than this beam balance?
It all comes down to the point whether how well do you calibrate the digital balance. One of the problem of digital devices is that this is a totally mechanical device. So if you know that this device is properly working, then you would have almost no problem, no electricity requirement to run this device. Whereas digital balance requires batteries or a DC supply or a AC supply for certain components, and then if they are miscalibrated, then it can also come down to the point that you might need some trained technician to recalibrate that if it's not very easily accessible for mass people. Whereas these devices can be very easily maintained and operated. So this mass, so you see over here, this left side, this is basically used to for error adjustment for this whole device. So you can turn off this screw left or right to make it a bit out or a bit inside, so that you can always have a perfect calibration for the masses on both sides. Do you guys understand how to devise a calibration? Do you know what does it mean to calibrate something? Because it's a measurement chapter, I might as well talk about that. Do you understand? Do you guys properly understand what does this word calibration mean? Someone? Anyone?
Like adjusting the true values.
Sir, maybe not, sir.
Like
Maybe you
adjusting
do.
it to verify if accurate.
You do have some ideas because you know this word, so you might have some understanding for what calibration is. Let me just clarify or refresh your memories if you know it correctly as well. Calibrating a measurement device means to make it capable in general terms. This is not a Wikipedia definition, it's just what my understanding is. To make it capable to measure a certain unknown quantity accurately. That's basically what calibration means. For example, the first example where this word calibration came to you in your O-level syllabus was when we came across the chapter thermometer. How can we make a thermometer from scratch? We're gonna have we need to have a mercury thermometer that is already prefabricated. I'm not telling you how to fabricate a thermometer because that's something that you might know. If you are interested, you can look it up in Google and YouTube, how a mercury thermometer is actually made, how the mercury is put into that thin glass wall bulb. But I'm disregarding that process. Let's say you have a thermometer body which with no markings on its side. You have no calibration on its side. If you really want to calibrate that, what do? We first put it into crushed ice, which is put into a funnel, wait long enough so that the mercury level goes to the lowest possible level. You give it a mark, and then you place it onto boiling steam. That boiling steam environment should be maintained with a cover, and that which should be attached to a manometer, so that you can make sure that the pressure within that steam container is also exactly at 1 atmospheric pressure, because the boiling temperature of water can be significantly varied by the pressure it experiences. So we have that whole entrapment of steam, so that steam simply doesn't evaporate out to the atmosphere, because that would give you not enough temperature, providing a hot environment. And then we allow enough time for the thermometer mercury level to rise long enough, and we give it a mark at the stable mark. This is considered to be 100 degrees Celsius. So you know that there are two fixed values, and then you can divide the whole gap in between them into equal convenient pieces. I'm using the word convenient because a typical thermometer, we say that we divide it into 100 equal pieces. Each length, each division gives us 1 degree Celsius. Well, it can so happen you can have a pretty long thermometer where you might be able to divide that whole space in between in 200 pieces, let's say. So that way you can have half degree fraction. Or if your thermometer is not that long, you might divide this into maybe 50 pieces. So each division in this case is going to give you 2 degree Celsius. So it all comes down to the point that how we are going to measure that. Sometimes it can also be a good idea that if your thermometer is not really long, let me just draw this to you. If your thermometer is really not that long, and you really still want to have a high precision value, let's say this is a thermometer and this the stem goes up like this. Let's say this is 100 degrees Celsius mark, this is 0 degrees Celsius mark. If the thermometer is not so long that you cannot put multiple marks directly on the same side by side, so that they're going to become too much clumsy or too much close for the reader to later read on, one logical way we can also go for is that we can give the full degree Celsius mark on one side and the fractions on the other side, pretty much like how the linear scale for a micrometer screw gauge looks like. If you remember, in the micrometer screw gauge, on above the reference line, we have all the full millimeter mark, 0, 1, 2, 3, 4 millimeter, whereas on the lower side we have the half millimeter mark. So it is also possible that we can give alternate marks on both sides, just to give us a bit more spacing between the values, and also to have a higher accuracy. This is also appreciated or can be achieved. Some thermometers can also have two different type of temperature marking. For example, some thermometers can be designed to have degree Celsius on one side and degree Fahrenheit on the other side. So that can be also useful in some cases. The whole idea of calibration is to make the device usable for measurement. Now, how do we calibrate, or how do we in this case, this is essentially meant to check for error. I mean, for example, let's say you are provided at this device, you're about to take some measurement with this device. How would you measure that amount to a very precise amount? So to do that, in the first place, you first have to know that this device works perfectly. It means that if you place an object of known mass on the left side, you should be able to get that exact mass on the other side as well. The logical way to check the error that might exist within an equipment is always that we place a known mass onto this mass side. In this case, it's a single pin balance. This can also work for a beam balance as well. Yeah, beam balance usually is seen to be pretty balanced, because if you don't load anything, you just look at it, you should be able to see it perfectly horizontal. So beam balance typically doesn't get any zero error because it's so widely visible whether it has zero error or not. Where
Sir, isn't it like prone to human error?
which one? This device?
Yes, sir.
Yeah, every measurement is prone to human error as long as humans are reading it, because I mean, like I said, that let's say these big masses are going for, let's say this is 100 gram, this is 200 gram, this is 300 gram, or maybe this is 100 0, this is 100, this is 200, and then here you might have, let's say another 100 gram. So 0, 10, 20, 30, 40, 50, 60. Then you have the divisions of 10 grams over here, then you have the divisions of 1 grams over here, and this is the and here you have the divisions of 1 gram over here in 0.01 gram. So altogether, if you sum up the whole thing, I mean, if you place everything on the right side, the total amount of grams you might measure is 300, then sorry 200 from the top side. So let me just select this and maybe put it on the paint so that we can do some. So this one is typically the way this should measure. This is 0. Currently this is at 0 gram. This is your 100 gram, and this is your 200 gram. Whereas this second scale, this is 100 gram value. So let me use a different color, maybe red. This is 100 gram, which means now it's 0. Then you're gonna have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 gram, and the 100 gram on the second scale. And then you have 10 grams over here, which means it already shows 10 grams. I'm not writing this, so it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 grams. And then you can have 0.01 gram, because here this thing is, every 10 division is 0.1 gram. So the smallest division that we have to move this thing is 0.01 gram. So this is only 1 gram over here. So if you move everything to the right side, the total amount of mass you could possibly measure is 200, 100, 10, and 1. So altogether, your maximum capacity that you can measure is 311 grams. Human error is always possible. You can always place a certain load at a certain location and read it wrong. I mean, you're not supposed to, or a person who is doing the experiment is not supposed to, but they could always do that. They can place it in the 5 place, they might read it as 4. They might place it in the 100 place, they might read it as 200. They might place it as at the 0 point. I mean, taking a reading of a visible scale and making a mess while doing this is not so quite uncommon for human beings. Let me just put it that way. Does it make sense?
You said that placing the biggest possible mass and then bringing everything to the right hand side, sir. So I mean, everything is done by means of calculation, right, sir? I mean, after one skill gone, then another.
Well, we don't actually do much calculation here other than adding the individual mass label by the individual masses. For example, you just have to, whatever the object that you place over here, and then you have to slide it onto the individual notches and adjust the balance perfectly so that you can have a perfect horizontal level. And then you just add up all the different numbers. For example, let's see if you have placed it at the 100 gram mark, the second one at the 4th mark, the third one at the 6th mark, and this one at some fraction. You just add up all those values. So 100 plus maybe 60, then maybe 4, then maybe 0.045, something like that. So you add up all those things and you get a perfect measurement. It's just basic addition. But if someone makes a mess up while reading any of those 4 different scales that we have, the large one, big one, smallest one, then they are definitely gonna get a wrong value. That's basically human error.
Sir, my question was like, I'm thinking it like the thermometer, like we are dividing marking the tube of the thermometer in 100 equal markings. So is it like that, like in the beam balance, you're placing markings equally?
Well, they have not actually marked this thing exactly equally. What they are trying to achieve here is to have uniform fractions of higher mass on the lower scale. So this, but the idea is pretty much the same. You can measure total amount of mass on the left side, which should be equal on the total amount of mass dictated on the right side. The weight of the devices that we have over here are also incorporated. So that's why you have a length over here where these masses are pretty close. You can see over here that when you have kept these masses right over here, your total amount of weight over here is this much, where the rails are also involved, where the total amount of mass over here is this much plus the total weight of this whole hanging contraption. So together they are supposed to give you perfectly balanced weight, which should be 0 on this side if nothing is loaded here. If it is not 0, we can move this thing out or closer left. The question that you're asking, that whether this device is similar to that part, it is definitely somewhat similar. The idea is quite similar, but it works on a much more higher working level. For example, within the thermometer, you do not have the opportunity to go for a really high precision like this, because if whatever your markings are, you are limited by that value, pretty much like a meter rule like that. But let's say if you think for the micrometer screw gauge, within the micrometer screw gauge, you have two different scales running for you. You have a linear scale where you can measure a half of a millimeter. Then you have a circular scale where you can measure up to 0.01 millimeter. So using these two scales, you can take a pretty precise measurement. Whereas in this case, you have 4 different scales running for you. So you can take up values up to 5 decimal of 5 significant figure. Try to understand, this thing has a capacity of 311 gram and a sensitivity of 0.0. So it's very much possible you might get a reading of, let's say, 264.41 gram for a specific measurement. That's a 5SF value. So the principle, in principle, they work in the same way, but this has much higher capability built within itself. I'm going to put it that way. Make sense?
Yes.
So do all of you understand how to use this device somewhat? This similar mechanism is also used to measure very large amount of rods. I mean, if I just show you one of this rod measuring device, iron balance, is that a good word?
Sir,
আমি তোমাদেরকে different balance গুলো দেখাচ্ছি এই জন্য no হ্যাঁ ইউসুফ বলো।
Sir, the beam balance you showed, sir, it works with by means of an spring, because of which we are getting these readings, right? Like a Newton meter.
In the Newton meter, yes, we rely on a spring, on the spring constant. That yeah, we rely on. Yeah, answer to your question is yes. On a spring, but on a Newton meter, we depend on a spring. Yes.
I mean, the working principle of the beam balance you showed is also the same, right, sir?
With Newton meter?
No, sir. The beam balance you just showed.
Yeah. This is also actually a beam balance because we have a beam, but this is a beam balance with only one holding pan, one pan. So you have the measurement on the right side, you have the holding pan on the left side. Benefit is that you can just slide it. These masses are not going anywhere and directly get the measurement. So all the batkaras or the measurement stones are actually built in within the device. That's the benefit of it.
I mean, instead of the measuring stones, we have springs to adjust the movement of the scale.
No,
sorry,
usually in spring balances, we do not have this kind of sliding masses. We only have the spring and a calibrated scale that gives us the measurement. And pretty much the only thing that you can adjust within a spring balance is the zero error. You cannot recalibrate or strengthen or weaken the spring. Well, you can definitely weaken the spring beyond its elastic limit. If you just pull it out of its box and pull it too much, then your device is going to become dysfunctional. But you cannot essentially change, recalibrate the spring to so that you have to use a different scale printed on the device. That usually doesn't work, and it doesn't have sliding masses. But the read-off is pretty much the same, that you have a sliding marker that goes onto a scale. I can actually show you. Actually, let me just try a different. Yeah, something like that. This is how a spring balance looks. So inside there is a spring, and this mark is over here, which is this red mark over here. And if we pull it down, this spring is gonna start getting compressed. And this is working with a compression spring. Sometimes it can be also lengthening spring. Different spring can work in different designs, but that's pretty much the idea. The further you compress it, the more readings you're gonna get over here. কি জানি দেখার জন্য ঘুরতেছিলাম, আচ্ছা রড ব্যালেন্স, রড মেজারিং can't seem to find it. Yeah, got it. This is a good image. I have all the devices over. Okay, this is actually not a very high resolution image, but typically these are the devices that you might have seen somewhere in the bhangarid dokan or in the junkyard. They use this kind of devices which can give you a digital measurement of a very large amount, maybe in excess of tons. They can measure this. This is what I call this is called platform balance. I didn't know this name. I really didn't. But these are also pretty much like top end balance. You have a surface where you load your stuff and you can get the reading out of it. The other thing that I was talking about was, what was that? Lever balance. Lever balance. What was lever balance? Yeah. I have a reason to show you all of these devices because eventually, hopefully, you pass your AS. I hope that happens for all of you, each of you. And you eventually are gonna get to A2. And for the paper 5, it's important that you have a holistic idea for the lab equipments, even for equipment that you have never touched or you have never seen in your actual lab, but you need to have an idea how equipment works for you to be able to incorporate those equipments in your actual description. That's important. So, because internet is so available right now and we have so much information going around, if someone assumes that you're supposed to know something that and then you don't, you cannot really catch them off guard. They might be actually correct. So this is one of those lever balance, actually how it looks like. See, there is a circular mark over here. The way it works is pretty simple. This is actually an adjustment mass. You have to put the object over here. This pan is made sure to go only vertically by the help of this and this. So if you apply some load over here, this is going to only go down. And as this one goes down, because this arm is going to go down, so this arm is going to go up. So this mass is going to be lifted up and eventually it should give you some reading over here. So you have two set of readings over here. You should take reading from both of them. And then that pretty much gives you the very basic of the idea. The purpose of this mass is to keep it at a certain place so that this thing is properly calibrated. How do we calibrate a certain sketch? I actually moved off from the idea of calibration. How do you calibrate a certain device? Or let's say you are provided a certain measurement device. Let's say you're provided okay. Just a second. Let's say you are provided this scale and you are asked to measure something. You know how to use this device pretty well. And when nothing is loaded, you can see that this thing does not have any zero error in it. So you are pretty happy with it. Open image in new. Why I did not do that? What did I do? Open image in new. Okay. So maybe let's say you are provided this device and you know how to use this device and you can see there is no zero error, but there might be some calibration error. Calibration error means that if these two arms are not properly perfectly balanced, if they are not perfectly balanced, because you can always have some friction in the pivot which can actually go against you the precision requirement for your experiment, because frictions tend to stick up to objects. So you might always have some sort of a biased reading in your measurement, which you want to avoid smartly. So one of the things is that the typical way how we actually check the calibration of a device is that we place a known measurement on the device. We load the measurement device with a known measurement. For example, let's say you have some mass in your laboratory which are labeled 100 gram, or maybe they are labeled 100.00 gram. So you know that these masses were made, and these masses are definitely to be stored in a very careful environment within a very humidity controlled and good boxes, so that they don't lose their a value by reacting to air or something else. So if you have a mass in a laboratory, which many laboratories do have, and then that says 100.00 gram, then you know that this mass is calibrated 100.00 gram. So you can just put it right over here, and you can actually check the value of that thing by moving two different things. So you can either move the second thing all the way to the right, that should give you perfect 100, or you can move only the first one, the big one, to the center, which also gives you 100 gram. Now, if you put a known object that you know from someplace else, from someplace more dependable than this device, and put it on the device and measure that mass, and if you see that the mass measured by this device is exactly same as your pre-known value, then you know that the calibration of this device is perfect. That's basically how we check it. That checking a device with a known value, and if they are comparable in this case mean they are within approximately close acceptable limit. I mean, it can also happen that some devices might not give you the exact same value that you know for to be true, but the error that you are getting is too small to be that you can practically ignore it. That can also happen. That actually comes down to the point of your judgment that whether a certain measurement can be accepted or not. But if it is within comparable limits, then you can say the calibration of this device is good. You don't have to bother about it, and you can just go ahead and use this device. This is equally applicable for all other measurement devices as well. For example, ammeters, voltmeters, joule meters, coulomb meters, anemometers, you name anything that measures anything can be used to measure, can be used to check whether it gives a correct reading or not by measuring a pre-known correct value. Taki, you are about to ask a question.
স্যার আপনি যে বলছিলেন যে আমাদের একটা ডিভাইস ইউজ করার কেমনে ইউজ করতে এটা লিখতে হতে পারে মাঝে মাঝে। স্যার আমাদের তো একটা ডিভাইস কিভাবে চলে ওটার জন্য একটা পার্টসের নাম জানতে হবে। তা এখানে তো আমি একটা পার্টসের নাম জানি না এখানে।
No. You never have to mention how a device works. If I said it wrong. If I didn't say it, then you understood it wrong. Either way, you never have to say how a device does its job. You just have to know which device to use in what purposes. For example, an anemometer measures the speed of air. Micrometer screw gauge measures the length to a very high precision. And then let's say a Hall probe or a Hall voltage meter measures the magnetic flux intensity or magnetic field strength within a certain region. You have to know the name of multiple devices which works for certain multiple purposes, but you do not have to be able to specify that how the device's internal mechanism works. Rather, in many cases or in some cases, you might have to actually mention how to use that device in regard with the experiment. For example, let's say you are trying to measure an angle within an experiment. Try to get this idea. You're trying to measure an angle within an experiment. You can use a protractor. Are you going to use a basic geometry box protractor that you have? It has only 100 degrees within itself. Maybe you can. Maybe that's a sufficient requirement. Or maybe you can go for a much bigger protractor which has which has smaller fractions inscribed on its circumference, maybe half degree, maybe quarter of a degree. You can actually buy these protectors which are bigger in size, and because the protector is large, you have a larger circumference of the half arc or maybe the full circle arc. Circular protectors are also available to buy, and because you have a larger length, you can actually make it more smaller fractions on the edge. Or maybe it's also possible that you are choosing not to use a protector altogether. You are going to measure the angle by measuring two different distances. You can take any of the three distances: opposite, adjacent, or hypotenuse, whichever two are convenient for you to measure for that experimental setup. And then you can go for a trigonometric equation to measure that angle, calculate that angle. That can also work. You don't have to mention how the device works. You have to just mention how to use that device in respect with that experiment. Does this idea make sense? Make sense?
Yes, sir. স্যার কিন্তু আমরা যখন বুঝাবো যে ডিভাইস কিভাবে ইউজ করতে হবে, তখন তো ওদের পার্টসের কিছু মেনশন, পার্টসের নাম তো আসেই স্যার। যেরকম স্যার মাইক্রোমিটারে তো আমরা থিম্বল পরে র্যাচেট এইগুলো মেনশন করি আনসার।
No, you don't have to go in the explicit details of those. I mean, if you are ever to measure a micrometer screw gauge, let's say for micrometer screw gauge, you just have to say that we use a micrometer screw gauge to measure the diameter of a certain wire. Let's say if it's a wire and you're measuring diameter, and then you also have to say that before using the micrometer screw gauge, we check the device for zero errors and correct every reading if there is any zero error. and we also take the diameter measurement in multiple different places, in multiple different orientations, and average all of those data to get a more reliable value for the diameter. That's all you have to say. How do we use the microscope gauge? I mean, the main scale reading, the thermal scale, the ratchet clicks, and then we look for the closest attachment, and then this is the formula that works for the microscope gauge. No, you don't have to go into the details. So মানে অতটুকু লাগবে না. You have to just say that how to use the device for the requirement.
Okay, good.
Beautiful. So yeah. আচ্ছা, লিভার ব্যালেন্সের আইডিয়া, আইডিয়াটা জানি কই গেল? লিভার ব্যালেন্স আইডিয়াটা কি বুঝে গেছে বলবান? মানে how does this work? This goes down, this goes up, and how much this should go up is controlled by where this stationary mass is located. You can move this mass by you can see in different figures, it's in different places. Here it is at this point, in other figures here at the lowest point. So this can be in a lot of different places depending upon how you need to calibrate your device. So this is basically your calibrating component, and then this can go up and down, and you can take readings out of it. This is what we call a lever balance.
Sir, ওইটা মুভ করতে পারবো না, if like সকেটটা এটা দিছে ওইটা যদি মুভ করে তাহলে তো
বলতেছি এইটা হচ্ছে this calibrating mass should be used not every time you do a measurement. Let's say you are trying to check whether where this, I mean, let's say you just bought this device. This thing came in a box which was disassembled. So you have put now everything, frame, the scale, the pan, everything over here. You have put everything over here. Now you can see over here there is also an additional hook over here. The reason we have a hook is because sometimes we need to hang objects other than placing them onto an object. That can also happen. So you can actually have objects hanging over here. Anyway, point that I'm trying to make. You are going to use this device, let's say at the very beginning, when you are trying to set up the scale for the first time. So you are going to put some appropriate weight over here, known weight over here, or mass over here, which produces a weight over here. So you place a known object over here of known mass, and then you find out that where this calibrating mass should be on this arm length, so that you get that exact value where this thing is perfectly balanced on its own. So you have to find out that sweet spot where it should be, that this one goes down, so this one should go up, but how moving it by how much actually gives us a correct reading. So then you have to read that off. And also, if you have a look at this scale, I mean, let me just copy this image. Is it big enough image? No. Is this big enough? This is a bit bigger or a bit more clear. Let me just show you one more thing, which is going to be interesting for some of the MCQs which we're going to solve just after a while. I can delete this. Okay. If you have a good look over here, you should see that the spacings are getting squashed. Have a look. You can see over here, these are all 150, 200, 250. You can see as you slowly are going up, the gaps over here are becoming smaller. Do you see that? I mean, the scale is more squashed on this side than it is over here.
Yes, sir.
The reason it is in this pattern is because of the curvature of arc. You can see that the moment always works for the perpendicular distance, right? So whenever you're going to load some object over here, this weight currently is working vertically down. So here is a pivot point. So currently the total amount of vertical distance is this much. The further it moves up, your horizontal distance slowly becomes bigger, right? Try to understand that. And also this arm side is at a different angle. So let's say whenever it comes down to about halfway mark over here, let me just draw maybe. So let's say whenever this arm comes somewhere over here, this arm is almost perfectly horizontal. So that's where you get the maximum moment out of the load, but you are still not getting the maximum load out of the balancing weight. If this slide goes even down for a bigger mass maybe, then this arm is gonna go further down and is gonna get closer, because you have to understand that this pivot point is gonna go around in a circular arc. So at the horizontal position, you're gonna get the maximum horizontal, maximum perpendicular distance. As it's gonna go down below the horizontal mark, the perpendicular distance is gonna become smaller. So as the perpendicular distance becomes smaller, you have a less moment produced by this, which is currently now being measured or being balanced by a much higher moment, because now this mass is still on its way up. So this one's perpendicular distance is still increasing, still increasing. So you have to compensate for that dissimilarity within the scale. That's why the fractions are small over here, but the fractions are large over here. Does it make
স্যার
sense?
কেমনে কম্পেনসেট হচ্ছে?
মানে হচ্ছে যখন আমাদের এই ওয়েটের মোমেন্ট কমে যাওয়া শুরু করবে তখনও কিন্তু এই ওয়েটের মোমেন্ট ইকুয়ালি কমবে না। I mean, what happens for an actual beam balance? Let me just help you understand. In an actual beam balance, you have two beams on two sides of it. You have two hanging pallak English কি বলে? Pallak English. You have two pans. You have two pans on two sides of the beam, and the perpendicular distances are equal on both sides. Whenever you place something, one side goes down. Let's say if one of the side goes down, so let's say this side is going to go down, let's say. So this is going to go up, this is going to go down. So they're both going to move by same angle. So you're going to have proportionally the same amount of reduction of moment, because now let's say the pan is over here. So this was the initial perpendicular distance for a pretty long distance. Now the perpendicular distance is only this much. Whereas for this hanging side as well, the perpendicular distance has reduced by the same proportion. Do you see it? Because it's a horizontal beam. But that's not the
Yes.
case over here, because there's a curve over here. So that when this beam actually moves down to maximum and then starts to get smaller, this mass has not lifted up all the way. This is still have this mass still has space to go further up, which means the moment produced by this weight is going to slowly become less beyond the horizontal position of this pivot, where this one's moment is still going to increase because of the angular because of the angle that is involved over here. Because these two sides, I mean this one, let me use green, because this side and this side, they are not on a single straight line, so they have different proportions of increase and decrease. So that reducing moment problem is compensated within the scale.
Sir, it is just because of
Which is
this being curved, we are not able to get, I mean, more accurate results. So
It's no,
instead of
it's not about accuracy. I'm just saying that why the scale is like that. Why do we have big gaps over here and small gaps over here? What's the purpose of this? You can have accurate results depending upon how you have calibrated the device, how small of a mass you are measuring, how many divisions do you have. Getting an accurate result is something else. But I'm telling you why the scale is non-linear. Why do you have a different amount of gaps in different places along the scale? That's what I'm saying. You can get accurate results. So I stopped you in halfway in the question, which I shouldn't have done, but I'm sorry. Please, could you please finish your question?
Sir, I mean, because it is curved, we are not getting, I mean, linear gaps.
Exactly, precisely the sentence that is correct. So if I just go jump into one of these examples that we have over here, which we have in the graph segment of this MCQ paper, you should be able to see many of these examples. Where are those? Here we are. Let's say this is one of the, is this the first one? Yeah, apparently that is the first one. So take a look at this question. This is 1.43, I believe.
1.4.
Oh, it's 1.4, question number 21. Have a look at this question. If you have the MCQ book, you can turn it over, or if it's convenient for you to see from the screen, you can also see it from here. Your choice, no big deal. Have a look at this question. What does it say? The deflection of the needle of an ammeter varies with the current passing through the ammeter as shown in the graph. So try to understand. Current is increasing, and that increase is shown in the horizontal scale, but the deflation of the ammeter needle is shown in the vertical scale. And you can see that these two things are not equal, or not proportional. They have a bit of a curve within them. So curve, do you know how these type of equations are generally written in math? I mean, this thing. The most common variation for these equations is like this: y equals to ax to the power b. You could have any values over here. You could have any values over here. It doesn't have to be root x. It could be 1/3 x to the power 1/3. It could be x to the power 1/4 x to the x to the power. What can I say? Something less than 1. That is, if you are losing gradient, this power has to be something less than 1, not negative. That's all that is. So anything smaller than 1 and bigger than 0 is okay for a losing gradient curve. And this A actually tells us that how fast it is going up or down. This might be 1, this might be some number. And because this one graph was going through the origin, it doesn't have any y-axis intercept. However, if it did not go through the origin, we might as well have some y-axis intercept. This is the very basic expression for any curve that follows a pattern. Follows a pattern means that doesn't go like this. It has a single pattern like that, like a decreasing gradient or increasing. So this is the most common type of unknown format. Then you can slowly use multiple different processes to find out the values of this A, B, and C if they are involved, and actually develop the equation. Not relevant for this question, but I just wanted to share that. Now you have to choose which diagram could represent the appearance of the scale of this meter. Now try to understand, or try to solve this question on your own and see if you can solve it. I'll give you 1 minute.
Sir, Parsi.
আচ্ছা একটু ওয়েট করো তাহলে সবার জন্য, or maybe 2 minutes. Judge each one of the MCQ choices. Judge each one of the MCQ choices. You have to understand that the graph doesn't have any scale labeled on it. It's only the name of the two axes. So use your imagination and try to understand.
Thanks.
Sir, Parsi.
Okay, so which one do you think is the correct response?
A.
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 A is the correct response. So do you all understand how?
Yes.
Yes, sir.
No, sir.
I'll help you understand. What do you need to see for this? Let me just copy this and put it on the whiteboard maybe. Zoom in. Okay. So what you need to see that, let's say the current scale is going to be uniformly calibrated like that. Okay. And the diffraction of the ammeter needle will also be on the axis. It's going to be uniformly calibrated. So it's going to be equal spacing. The scale is not squashed. The question is saying that which diagram could represent the appearance on the scale of this ammeter. Ammeter scale, analog ammeter scale actually moves like on a curve, on an arc to be more accurately. So what you need to see that when the increase of the current is close to 0. So let's say let me use a different color, red. So for this much increase of current, you have, let's say, about this much increase of the deflection. As your current increases by the same amount over and over on the x-axis, would you have the same amount of vertical gain on the ammeter? So try to understand the behavior of this curve. What this actually shows that as you slowly go on the farther increased value of current, your vertical gain is gonna slowly become smaller for the same amount of increase, because that's the whole idea of a decreasing gradient curve, that you get a much higher increase at the beginning and then your delta y by delta x become much smaller. Does it make sense? For the same amount of delta x, you're not going to get the same amount of delta y as you used to have for a more steeper part, which means your deflation of the ammeter needle, this part is slowly becoming smaller for the same amount of increase of current. So you're going to have less deflection for the same amount of increase of current when the current value is quite large. I'm going to say this sentence again. Hear me out. You're going to get, when the current value is on the high end, for a high current value, for the equal amount of increase of current, your amount of deflection is going to become smaller. So you have a much bigger deflation for the 0 to 1, a bit smaller on 1 to 2, a bit smaller on 2 to 3, a bit smaller on 3 to 4, and that pattern follows, which means that you're gonna have a smaller increment of angle for the same amount of increase of current. বুঝা গেছে?
জি
Yusuf?
Sir, I mean, can you show by means of different graphs as well?
Yeah, I'm just gonna cover all the other MCQ choices over here. So if I just go for option choice B, have a look at B. What does B shows you? It shows you that for initially you're gonna have a small deflection, later you're gonna have a large deflection, which means if you have the same axis of this thing, let's say deflection on the y-axis and current on the x-axis, for this curve, for this type of scale, your curve is supposed to look like this, of an increasing gradient. So initially for the same amount of horizontal increase, you have a small amount of increase on the y-axis, but later when you have that same amount of, let's say, horizontal axis, your vertical gain becomes pretty significantly large. বুঝাচ্ছে?
Yes, sir.
Beautiful.
I mean, sir, increasing gradient means increasing
Gap.
yeah.
Beautiful. How would the graph of C look like? Can someone guess?
স্যার
প্রথমে একটু কার্ভ এরপরে আবার
Well, it's going to be curved for sure, but how would you
মাঝখান
describe the
দিয়ে
curve?
গ্রেডিয়েন্টটা কমে যাবে, পরে আবার বেড়ে যাবে অনেক এক্সপোনেনশিয়ালি।
So for
Sir,
the first half, you're going to have one type of behavior. For the second half, you're going to have a different behavior. What behavior do you get for the
Yes,
first
sir.
half? এইটুকুর জন্য
increasing gradient and constant
এইটুকুর জন্য হচ্ছে decreasing gradient. Then you're going to have a bit of a constant gradient, maybe from 4 to 6. That remains constant. And then from over here, you're going to have an increasing gradient, right? So C graph might look like this. Boink. Make sense?
yes, sir.
Yes.
And D would just look the other way around. So like that. Increasing for the first part and then decreasing for the second. So that's how different curves can be used. I mean, even if a variable that does not change with the physical measurement equipment linearly. I mean, that was one of the key requirement. That is one of the preferable requirement. I'm not going to say essential. I'm going to say preferable. That is one of the preferable criterion to design any equipment or measuring device, that we should preferably have a linear relationship so that our scale is linear. But in any case, in some cases, if the measurement quantity is something that we want to use, but the behavior or the change of that physical quantity is not actually linear, then we can actually reshape the scale to accommodate for that change. One of the examples that I'm going to tell you is that among all the thermometers that we have discussed, high temperature measurement, to measure high temperature, there are only two types of thermometers that we can use. One is the thermocouple thermometer, where you can still use contact, and locations where we cannot use contact, we have to use pyrometer. Pyrometers are actually faraway thermometers, which actually measures the infrared radiation coming out of an object and converts that infrared radiation by some mathematical equation or by some graph manipulation into the surface temperature where you are aiming at it. So the way these things work, the physical equation on which these two type of thermometers, thermocouple thermometer or also the pyrothermometer, the way they work, they do not work on linear equations. They have exponentials and y-axis intercept and so on and so forth, and they work with these values. But because we prefer to use those mechanisms, or maybe we are out of convenient options to measure those temperature, we still prefer to use those equations, because manipulating an equation is usually pretty easier compared to developing a totally new type of measurement technique, which might not be useful or easy or may not be reproducible for mass production. Do I make sense? Maybe not.
Yes sir, yes.
Okay, if we go for some other MCQ questions over here, if you kids have any other problem, please shoot from 1.2. Anyone have any question from 1.2? Anyone? Oh, this was from 1.4, my bad.
স্যার 4 এ একটা আছে
আচ্ছা আমি একটু সিকোয়েন্সিয়ালি যাই 1.2 থেকে কার কোনো প্রবলেম নাই 1.3 থেকে কার কোনো প্রবলেম আছে anyone to ask anything from 1.3 1.3 is all calculation
নাম্বার 1 টাই স্যার নাম্বার 1 টাই আছে 1.3 তে জি
আচ্ছা
স্যার
দেখতেছি সমস্যা নাই this question says that the power loss of P in a resistor is calculated using the formula P equals to V squared divided by R. The uncertainty of in the potential difference is V is 3%. Uncertainty of the resistance is 2%. What is the uncertainty in P? So this is the equation P equals to V squared by R. So if we're gonna calculate the fractional uncertainty or the percentage uncertainty, fractional uncertainty or percentage uncertainty pretty much work in the same way. So delta P by P would be twice delta V by V because there's a square over here plus delta R by R. The same thing can be said for percentages as well. So I'm going to simply place all the percentage uncertainty in this expression. So 2 times 3% plus 2%. That gives you 8%. বুঝে গেছে?
বুঝছি স্যার জি
Beautiful.
স্যার বুঝতে পারছি
নাম্বার
Ah,
2 তে
Number 10.
number 10.
স্যার 2 তে 2 ছিল
আচ্ছা 2 তে একটু পরে আসতেছি সমস্যা নাই 2 তে গিয়ে ঝামেলা হবে 2 এর এসএফ ডিসকাশন নিয়ে সবসময় প্রত্যেক ব্যাচে আমি কিছু ঝামেলা করি I cannot usually explain this very clearly আচ্ছা anyway তারপর 2 আলাপ করব don't worry a thermometer can be read and accurate can be
Number 10.
oh sorry
ওয়ান পয়েন্ট থ্রি তে বেশ ভালো প্রবলেম আছে
বলো একটা করে I'll help it's all calculation 1.3 is পুরোটাই হচ্ছে calculation you just have to work your way with calculator but still if you get stuck I'm here to help definitely in number 10 is in an experiment a radio controlled car takes 2.50 plus or minus 0.05 second to travel 40.0 plus or minus 0.1 meter what is the car's average speed and the uncertainty of its value acha average speed বের করা simple 40.0 divided by 2.50 both of these numbers are in 3SF so we can prefer to give the answer in 3SF as well we can so that number should be how much
So 16.
16
16.0 3SF 16.0 so 60.0 over here is available in B or C so A and D bad প্রথমে A and D are cancelled we are not going to go for them then if you can have to simply calculate the average uncertainty so that way to calculate so let me just take this out okay so if we just write this V equals to D over T so del V by V equals to del D by D plus del T by T that gives us 0.1 divided by 40.0 plus 0.05 divided by 2.50 this is a fractional uncertainty therefore delta V should be this thing whatever that is multiplied by 16.0 how much do you get my calculator
0.36.
you get 0.36
Yes.
Yes, sir.
you get 0.36 so finally we're going to write this thing in 3SF 16.0 plus or minus 1 decimal place comes 0.4 make sense
The dear answer বেশি accurate না
well that's the whole point we cannot increase the accuracy of an answer in the process of our calculation that is misrepresentation of data the variables that we did measure, they were both measured up to 3 SF values. In your final answer, you can give 2 SF, you can give 3 SF, or one more than 3 SF. There's an available format for saying, but in this case, you have 3 SF answers. This answer has 4 SF in it. So if you are providing the data, sorry, you cannot give one more. You can give one less. I'm sorry, I messed up. I misspoke. Whatever the smallest number of your SF in your raw data, you can either choose that exactly to be your final answer SF, or you can choose one less SF than that, and that is also okay. Is it one less or is it one more? I feel confused. I have to look it up. But my point is, because both of the raw data that we have provided over here are given in 3SF, we can very easily stick to 3SF value, and we should stick to 3SF value. Giving a 4SF number actually incurs or actually proposes that we have measured this data to a very high amount of precision, which we actually did not.
Sir, can you please show the working, please?
Sorry, I had opened the door. Bolo, কি বলছো?
Sir, একটু working টা একটু দেখাতে পারবেন স্যার?
Sure.
স্যার
Yes.
স্যার আমরা প্রবলেম চ্যাট বক্সে দিয়ে দিই।
চ্যাট বক্সে প্রবলেম দিলেও ওখান থেকে আমরা বাই করতে, হ্যাঁ দিতে পারো।
স্যার আমরা 16 দিয়ে মাল্টিপ্লাই কেন করেছিলাম স্যার?
Because what am I trying to find out in this case? Am I trying to find out the percentage uncertainty or fractional uncertainty or the absolute uncertainty? What is my end game, end goal?
Sir, absolute.
Beautiful, because I'm trying to get the absolute uncertainty. So have a look at this equation. This should be make sense. This is the whole equation for the fractional uncertainty. So if you're trying to get this del V out, what do you have to do? You have to multiply this whole thing by V, right?
Oh, yeah, yes.
Beautiful, that's it. So এরপর
স্যার 2
হ্যাঁ 2টা বলতেছি। A student makes measurement from which she calculates the speed of sound as 327.66 meters per second. She estimates that her result to be accurate to plus or minus 3%. Which of the following gives her result expressed to the appropriate number of significant figures? Okay, 3% of 327.66 is how much? 3% of 327.66.
9.81.
I need more.
9.8298
298.
9.8.
298.
Nine point eight two nine eight.
Okay. এটা কারেক্ট আনসার সি দেওয়া না?
জি স্যার।
জি স্যার।
I'm not actually sure how this question works out. This question has bugged me for years. One thing that I and a question in examination পুরো কিছু লেখা ছিল না. It was said that the more able candidates were able to solve it or something like that. And there was some book written in the examination report of this question. One thing that I believe, not essentially entirely sure, is that this 327.6 is it's essentially a very large decimal-based number to measure the speed of sound, because measuring the speed of sound actually would require some sort of distance measurement and then some sort of time measurement. If we're using echo, then it is v equals to 2d by t. If we're using one way, it's d by t. You know how it works, measuring the speed of sound. But the point is, if it has a uncertainty of plus or minus 3%, this is the absolute uncertainty that we get by calculation. Now, if you want to write for 3SF value, they have given what? 4SF. Okay, if we go for 3SF value, we might write this as 328 plus or minus 10. Do you understand why 10?
So যে absolute uncertainty
নো স্যার।
Because we have to get rid of this 0.8. Now, if you want to get rid of 0.8, you have to add 1 over here. So this doesn't remain 9 anymore. What does it become?
10।
So এখন এই ওয়ানটা দেখো, this one is not actually affecting the main number in its unit place. This one is coming to affect the number in its 10th place. So that's why they prefer it with 330 plus or minus 10. So you cannot essentially express this number in the 10 in the 3SF while having this absolute uncertainty becoming 10. So mentioning it in 2SF is more logical, because the value over here is 9.8. Does it make sense somewhat?
স্যার এইটা
No,
তো
sir.
নরমাল এক্সামে দিতে গেলে তো ভুলে যাব না স্যার, মানে এটা মনে থাকলে হবে।
Well, here is what you can remember. Hear me out. Ideally, the answers, we prefer all the numerical answers to give up to a maximum of 3SF or to a minimum of 2SF. That's the typical preference of SF that we have, unless otherwise mentioned in the question. Unless otherwise mentioned, this is very important. So if you attempt to express this number in 3SF, it by default becomes a 2SF variable uncertainty. that should tell you that writing this actually doesn't make much sense, because this ultimately affects the first 10th place. So maybe writing this much would make better sense. You are not supposed to memorize this, but just try to remember that even for your paper 2, your preferable significant figure is either 3SF or 2SF. So if you try to even achieve for a 3SF number, it automatically becomes a 2SF variable uncertainty.
Sir, like 330 সাথে আমরা যদি 10 plus minus 328 এর সাথে যদি 10 add করি স্যার তাহলে 338 হয়েছে তখন তো স্যার 340 হয়ে যায় না?
Yeah, exactly my point, that whenever you express the whole number into 2SF, your ultimate answer is what? 320 plus 320 through 340, ঠিক না? Whereas if you attempt this one as well, you're gonna get what? 318 through 338. That if this number converted to 3SF, 2SF is still 320, and this also 340. So it matches. That is okay.
জি স্যার
বুঝছো?
জি স্যার
আচ্ছা,
So 15.
1.4 এর 15.
Number 3.
নাম্বার 3, আচ্ছা নাম্বার 3 করে দেখাচ্ছি। Number 3 was in a simple electrical circuit, the current in a resistor is measured as 2.50 plus or minus 0.05 milliampere. The resistor is marked as having a value of 4.7 plus or minus 2%. If these values were to calculate the power dissipated in the resistor, what would be the percentage uncertainty in the value obtained? So we are trying to get the percentage uncertainty of power. So that's the important bit. Percentage uncertainty is basically fractional uncertainty, let's say del x by x into 100%. এটা হচ্ছে আমাদের percentage uncertainty basic expression. So to achieve this, we simply have to calculate the fractional uncertainty, or maybe the percentage uncertainty directly. We can do that as well. First, we write the equation that the power dissipated in an electrical circuit is given by P equals to I square R. That's a basic equation for power. Now, that would imply that del P by P is given by del I by I multiplied by 2 plus del R by R. So if I go for percentage uncertainty, I can write that percentage uncertainty of power can be given by twice the percentage uncertainty of current plus the percentage uncertainty of resistance. The question has already given us the percentage of resistance directly. It is 2%, so I can directly place it over here, 2%. And as for this one, I just have to do the calculation, which would be 2 times 0.05 divided by 2.50. Sorry, into 100%. এখন দেখো এটা কত আসে, 0.05 ভাগ 2.5।
4 আছে, 4% আছে এটা।
So this is 4% plus 2% gives you 6%.
স্যার এটা কি স্যার 2.50 হবে, মানে এটা তো মিলি অ্যাম্পিয়ারে দেওয়া স্যার।
Yeah, this is a milliampere. Yeah, বলো, বুঝি নাই, আরো বলো, কোশ্চেনটা বলো।
মিলি অ্যাম্পিয়ারে যে আছে স্যার, এটা কি ওকে স্যার, that it is in milli ampere?
For percentage uncertainty, it's definitely all right. But if you are trying to get the absolute uncertainty in watt unit or absolute uncertainty is you have to consider the units. But for fractional uncertainty or percentage uncertainty, is perfectly all right, because you are definitely dividing 1 milliampere with another milliampere. So you are crossing out the units anyway. So for division work, unit wouldn't matter. So for fractional uncertainty or for percentage uncertainty, unit is really not that important. But for absolute uncertainty, it definitely is. বুঝছো কি বলছি?
Yes sir, thank you sir.
Sure. তাকি কোনটা বলছিলা?
স্যার 15।
15. A student uses a digital ammeter to measure a current. The reading of the ammeter is found to fluctuate between 1.98 ampere plus or minus and 2.02 ampere. The manufacturer of the ammeter states that any reading has systematic uncertainty of plus or minus 1%. This is a good question. I would like all of you guys to star mark this question. 1.2, question number 15. There is certain new thing to understand from this question. Which value of the current should be quoted by the student? Now, let's try and understand this thing. The reading of the ammeter is found to fluctuate between 1.98 and 2.0 ampere. So you're given the two terminal values of the reading. You do not have all the in-between readings. So this is the only two number that is available to you. So you have to make your work with these available numbers. Considering these two numbers, we can simply get that the average current should be the average of these two. So that is 1.98 plus 2.02 divided by 2. So the average current gets 2.00 ampere. And then if you want to find out the uncertainty, the rule of thumb that we actually showed in the earlier class, that uncertainty can be found out by finding out the difference between maximum minus minimum and minimum divided by 2. So that basically gives you 2.02 minus 1.98 divided by 2, you get 0.02. So as just from the properties of the reading, the value, this is actually your random uncertainty. I'm saying random uncertainty because this uncertainty was developed because of the quality of the data. This 0.02 is the random uncertainty which is obtained from the quality of the data. Additional to that, the manufacturer of the ammeter states that any readings has a systematic uncertainty of plus or minus 1%, which means whatever reading you get, it can be errorful up to 1%. Now, the actual value of the reading, which is the average number, was 2.00. So we're going to calculate 1% of that reading, that is 2.00. This we can say to be the systematic uncertainty. And this one can be labeled as random uncertainty. So 1% of 2.00 gives you 0.02 ampere. It just happens these two numbers are same, but in many cases they might not be same. For this case they are. So you have two uncertainties involved. So the total uncertainty would be the adding of this. So that is 0.02 plus 0.02 leading up to 0.04 ampere. So the final answer should be 2.00 plus or minus 0.04 ampere. That's your final answer. দেখো বুঝা যাচ্ছে কিনা
স্যার?
So 0.04 কেমন আসছে একটু
অ্যাড করে
বুঝলাম না
স্যার
এখানকার একটা আসছে হচ্ছে এখান থেকে আর একটা আসছে এখান থেকে বলো তাকি
স্যার সিস্টেমেটিক আর র্যান্ডম আনসার এটাকে অ্যাড করতে হয় এটা তো আমরা কি সবসময় অ্যাড করি দুটাকে
errors will always add up to give us more errors. Uncertainties are always added because uncertainty basically is what is the maximum range of error. Within your experiment, by doing repeat and average, we try to compensate one type of error by another one. So that our best guess is that if we're taking 10 readings, maybe 5 of them are on the plus side, 5 of them are on the minus side. So if we average them out, maybe you are canceling them out. That's the whole point of repeat and average. But the mathematical representation of uncertainty is to show you what is the maximum possible error that the calculation might have had. That's why errors are always added or uncertainties are always added.
স্যার এখানে যে র্যান্ডম এররটা এটা তো সিস্টেমেটিক এররটার প্রুফ না একটা
No. এটা হচ্ছে যে এক্সপেরিমেন্ট করছে তার এক্সপেরিমেন্ট কোয়ালিটির উপর ডিপেন্ডেন্ট maybe the person did not wait enough for the device to become enough stable, or maybe they did the experiment for a really long time while the circuit was turned on so that the wires actually heated up and gave them this type of reading. Maybe, I don't know. This variation actually shows for the quality of the experiment with respect to how the person who was doing the experiment, to what quality did they achieve the experiment. Bolo, Yusuf.
So 0.04 টা কেমনে পেলেন আবার বুঝাতে পারবেন?
Oh yeah, I just added the two uncertainties. This is the random uncertainty right over here, which is the half of these two, half of the difference of these two numbers, and then 1% of the average value. This is 2.00. That came out to be my systematic uncertainty. So systematic uncertainty is 0.02 ampere. Random uncertainty is another 0.02 ampere. So I added this together to get the total uncertainty, which is 0.04.
স্যার আমরা অ্যাভারেজটাকে স্যার কেন করেছি স্যার এক্স্যাক্টলি?
কোনটা?
স্যার অ্যাভারেজ কেন করলাম আমরা স্যার?
Average করলাম ভ্যালুটা বের করার জন্য what should be the average reading of these two set of readings, because we only have these two numbers available. If we had more numbers available, we would have taken all the numbers and average.
স্যার যদি স্যার কোশ্চেনে যদি একটা পারফেক্ট ভ্যালু দেওয়া থাকতো, then we could excluding that step, we'll still need to add the uncertainty
বুঝিনি।
after finding it out.
আচ্ছা হ্যাঁ, আর এটা কি জন্য কোশ্চেন করতেছিলা?
স্যার নাম্বার 9
কি জন্য কোশ্চেন করতেছিলা? নাম্বার 9। আচ্ছা, এটা থেকে আর কারো কোনো কোশ্চেন আছে? এনিওয়ান?
স্যার
হ্যাঁ বলো।
ফ্লাকচুয়েটিং বলতে কি নিডলটা ভাইব্রেট করতেছে?
না, নিডলটা ভাইব্রেট করতেছে না। এটা এরকম হতে পারে যে the person measured the same reading multiple times, or maybe multiple people measured the same thing one time each. So they had different values for a current that should not have different values.
Oh, আচ্ছা এখন বুঝছি, র্যান্ডম you can
এইটাই। মুনাম কোনটা বলছো? 9?
স্যার 9 জি।
A thermometer can be read to an accuracy of can be read. What type of energy is that? Can read, can be used to read, can be read. A thermometer can be read. Oh, আচ্ছা হ্যাঁ ঠিক আছে তাও হয়। A thermometer can be read to an accuracy of plus or minus 0.5 degrees Celsius. That this thermometer is used to measure a temperature rise from 40 degrees Celsius to 100 degrees Celsius. What is the percent uncertainty in the measurement of the temperature rise? Now, important bit. They're asking us what is the percent uncertainty in the measurement of the temperature rise. A rise part important. What you have to understand, let's say these are the two theta values that we have available. If I use a different color, maybe blue, let's say theta 1 is 40 plus or minus 40 degree plus or minus 0.5 degree Celsius, and then theta 2 is 100 plus or minus 0.5 degree Celsius. This uncertainty is individually a property of each of these readings, but the moment you're trying to find out the delta theta, you have to find out the difference, theta 2 minus theta 1. So that would be 100 minus 40. So the actual numbers are getting subtracted, but the uncertainties always get added. Degree Celsius. So you get 60 plus or minus 1 degree Celsius. That's your uncertainty value for the, that's your expression for the delta theta. Now for the percent uncertainty, we just have to find out the fractional uncertainty. So that is delta theta, delta of delta theta divided by delta theta. That's the expression for the fractional uncertainty into 100%. So that basically is 1 by 60 into 100%, whatever you get from there. কত আসে দেখো?
1.666
দেখো মিলছে কিনা?
এটা কত নাম্বার কোশ্চেন?
1.2 এর কোশ্চেন নাম্বার 9।
জি স্যার মিলছে স্যার 9 ডি।
বাট এখন বুঝা গেছে কিনা?
জি স্যার বুঝতে পারছি।
স্টেপস গুলো একবার দেখো। মেইন আইডিয়াটা হচ্ছে এরপর অ্যাকচুয়ালি ডিফিকাল্ট না, বাট মেইন জিনিসটা হচ্ছে যে এখানে আনসারটেনিটি দুটো অ্যাড হবে, আনসার দুটো সেপারেট হবে না। সো হাফ এন্ড হাফ অ্যাড করে 1 হলো, তারপর জাস্ট বেসিক ডিভিশন এন্ড দেন মাল্টিপ্লাই বাই 100%। অলরাইট, আচ্ছা
এটা স্যার ম্যাথের নাম্বারটা কত স্যার, মানে কোথায় স্যার, মানে স্যার problem to sir?
আচ্ছা ওটা ডিসকাশন ক্লোজ করে ফেলেছে, নতুন নাম্বার বলো।
স্যার 1.4 এ
স্যার 1.3 17 আছে।
আচ্ছা 7 একটু পরে নিচ্ছি, একজনের একটু প্রবলেম নেই। তাকে কোনটা বলছো?
স্যার কোশ্চেন 4
কোশ্চেন নাম্বার 4। কোশ্চেন নাম্বার 4টা দেখি আমরা। 1.4 এর পেজ নাম্বার বলো, পেজ নাম্বার বলে সহজ হয়। পেজ নাম্বার হচ্ছে 14 of 21।
1
হ্যাঁ পেজ নাম্বার 14 কোশ্চেন 1.4 এর কোশ্চেন নাম্বার 4 দেখতেছি আমরা। Okay, the question says a light meter measures the intensity I of the light falling on it. Theory says that this varies as the inverse square of the distance d. Which graph of the result supports this theory? Acha. So it says that I is proportional to 1 upon d squared. এই থিওরি সাপোর্ট করার মতো অ্যাপ্রোপ্রিয়েট গ্রাফ কোনটা হবে? তুমি দেখো কোনটা এখানে অ্যাপ্রোপ্রিয়েট গ্রাফ হইতে পারে। First of all, if you are trying to plot I versus d, we are gonna have asymptote graph on both axes. Here you have a crossing, here you have a crossing. So এই দুইটাই বাদ, ঠিক আছে কিনা?
স্যার গ্রাফটা কেমন হওয়ার কথা স্যার?
গ্রাফটা হওয়ার কথা হচ্ছে I over d এরকম হওয়ার কথা। If you have confusion, I can use Desmos to help you plot.
মানে স্যার ইন্টারসেক্ট করবে না।
স্যার ইন্টারসেক্ট কেন করে না?
কারণ তুমি একটা জিনিস দেখো, মনে করো এখানে তোমার I equals to k into d square আসছে, ঠিক আছে? দেখাই আমি বুঝাচ্ছি কেন ইন্টারসেক্ট করবে না। I equals to k into 1 by d square আসছে। তুমি d এর একটা ভ্যালু বসাইলা, k এর যে কোন k এর ভ্যালু তো কোন একটা নন জিরো নাম্বার হবে, k cannot be 0. I should write k not equals to 0. তাহলে তো k 0 হলে তো ইকুয়েশনই ভ্যালিড হবে না। In this case k is considered to be positive, whatever. So d এর যে কোনো একটা ভ্যালু বসালে আর একটা ভ্যালু আসবে। But what you need to understand, the further big the d becomes, the smaller the 1 by d square ratio becomes. So I becomes smaller and smaller. তুমি d এর যত বড় ভ্যালুই বসাও না কেন, I এর খুব স্মল মিনিস্কুল একটা ভ্যালু থাকবে কিনা ম্যাথমেটিক্যালি?
ইয়েস স্যার।
So practically তো এটা কোনো সময় জিরো হচ্ছে না। If you place the d value to be infinite, if the value of d is infinite, which means if you go to up to infinite length on this axis, then you might have I equals to 0, which means these two lines, axis and the graph, they will actually merge at infinite distance. ঠিক না? They're actually getting closer. ওই জন্য আমরা that's why these two lines are gonna becoming asymptote. Asymptote means that they're getting closer but never actually merging.
স্যার কিন্তু ডি 0 হলে তো স্যার আই 0 হবে।
d 0 হলে I হবে infinity.
ও হ্যাঁ সরি হ্যাঁ।
ওইটাও তোমার ওই ক্রসিং করছে কোথায়? y axis ইনফিনিট হাইটে।
জি স্যার ঠিক আছে।
বুঝা গেছে?
জি স্যার।
তাহলে এই দুইটা গ্রাফ বাদ, এই গ্রাফটা প্র্যাকটিক্যালি দেখাচ্ছে হচ্ছে I proportional to minus d square, not inverse. This is a I versus d square graph with negative gradient, তাই না?
Yes sir.
Whereas this one is the appropriate graph because you can see over here, এটা হচ্ছে y, এটা হচ্ছে x, আর এটা হচ্ছে m. এই দেখো y equals to mx. I itself হচ্ছে y axis variable, 1 by d square পুরোটাই হচ্ছে x axis variable. So this whole thing is considered, not only the d square. Be careful to observe. 1 upon d square. All of this expression is considered to be the x variable, and then you have a y equals to mx expression, which gives you a straight line passes to the origin.
বুঝছি স্যার।
স্যার আমি বুঝলাম না এ আর বি ক্যান্সেল কেন, একটু আবার বললে ভালো হইতো।
আচ্ছা এই গ্রাফটা কেন অ্যাসিম্পটোট হয় এটা কি বুঝো বাই প্রপার্টি?
না স্যার।
আচ্ছা আমি একটা ইকুয়েশন লিখি, নিউমেরিক্যাল একটা ইকুয়েশন লিখি। মনে করো হচ্ছে লেটস সে y equals to 2 into 1 by x square, ঠিক আছে? x equals to 1 বসালে y এর ভ্যালু কত আসবে? 2 আসবে।
2 আসে।
x এর ভ্যালু 10 বসাইলে
1/50 0.02
x equals to 1 বসাইলে x equals to 1000 বসাইলে ঠিক না?
জি স্যার।
So what I'm trying to show you, x এর ভ্যালু যতই বড় করো কেন y এর ভ্যালু আস্তে আস্তে ছোট হচ্ছে, but for even bigger values of x you are always gonna get some value of y. The value of y is never actually becoming perfectly zero. Is it becoming zero?
নো স্যার।
তার মানে আলটিমেটলি আমি যদি এই গ্রাফটাকে এদিকে আস্তে আস্তে বাড়াতে থাকি, অ্যাকচুয়ালি কখনো কি আমার এই গ্রাফটা এই এক্সিস কে টাচ করতে পারবে ফর এনি
না স্যার।
ভ্যালু অফ b? পারবে না। সিমিলারলি তুমি যদি উল্টা দিকে জাজ করো, মনে করো x এর ভ্যালু যদি আস্তে আস্তে এখন ছোট করি, মনে করো হচ্ছে x এর ভ্যালু দিলাম হচ্ছে, লেটস সে ইউজ আ ডিফারেন্ট কালার মেবি, লেটস সে x ইকুয়ালস টু দিলাম হচ্ছে 0.1, তখন y এর ভ্যালু আসবে কত? 50 আসবে না? 200 আসবে, 200 আসবে। দেখো তো কত আসে?
200 আসে স্যার।
200 আসবে। x এর ভ্যালু যদি দেই হচ্ছে আরো ছোট, জাস্ট 0.01 দেই, তখন y ভ্যালু আসবে হচ্ছে 20000। x এর ভ্যালু যদি 0.001 দেই, y ভ্যালু আসবে হচ্ছে 2000 and it can go on further. পয়েন্ট I'm trying to show you যে x এর ভ্যালু যদি আস্তে আস্তে ছোট করতে থাকে, x এর ভ্যালু ছোট করা মানে কি হচ্ছে আমি এই d এক্সিস আস্তে 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 আরো কাছে আসতে থাকবো, x এর 0 কাছে আসতে থাকবো। সো x এর ভ্যালু অনেক ছোট হচ্ছে, y ভ্যালু আস্তে আস্তে বড় হচ্ছে, কিন্তু এইটা 0 হওয়া 0 যদি না হয়, তার মানে y এর ভ্যালু অ্যাকচুয়ালি কি হবে? অনেক বড় হবে না? x এর ভ্যালু যত ছোট হতে থাকবে y এর ভ্যালু তত কি হতে থাকবে? বড় হতে থাকবে।
বড় হতে থাকবে।
তার মানে হচ্ছে আমি যদি এই ইভেন্চুয়ালি এই এক্সিস এর লাইনেও কনসিডার করি, the further the x value becomes smaller, the bigger the y value becomes, which means for any measurable value of x, no matter how small, you're going to have a large enough value for y, but practically speaking this graph will also never cross this axis, কারণ গ্রাফটা ক্রস করতে হলে x এর ভ্যালু কি হতে হবে? 0 হতে হবে। আর x এর ভ্যালু যদি 0 বসাই দেই, তাহলে y এর ভ্যালু কত আসবে? x 0 হলে y এর ভ্যালু হয়ে যাবে কত? আনডিফাইন্ড, ঠিক না?
জি স্যার অবশ্যই।
তার মানে for a visible range of this graph it will never touch any of the axes. তুমি যত বড় করে আঁকো না কেন, there will be always some gap between the axis and the graph. That's what we call the idea asymptote. Asymptote মানে হচ্ছে the graph and the axis are becoming very close but they are actually never touching. Mathematically there is always a bit of a gap. So ওই জন্য by mathematical consideration these two graphs are wrong because এই অপশনে দেখানো আছে এখানে ইন্টারসেক্ট করছে, এই অপশন দেখানো আছে এখানে ইন্টারসেপ্ট করছে। এই গ্রাফটা কোনোভাবেই দুইটা এক্সিসে কোথাও ইন্টারসেপ্ট করার কথা না।
বুঝতে পারছি স্যার।
গুড। আচ্ছা, তারপর অন্য কেউ প্রবলেম দাও? এনিওয়ান এলস?
পেপার 2 তে আছে।
অ্যাঞ্জেলিকা, তুমি কি লর্ডের বোন?
না স্যার।
Okay, never mind. I had a student whose name is Lord. He was also, I think, something Ribeiro, then Lord. এখানে আর আলাপ করার মতো, আচ্ছা আমি এই কোশ্চেনটা নিয়ে একটু আলাপ করতে যাচ্ছি। এই কোশ্চেনটা একটা ভালো কোশ্চেন।
স্যার এটার পর ছুটি দেওয়া যাবে?
এটা 27। আচ্ছা ঠিক আছে, আমি নেক্সট ক্লাসে এমসিকিউ নিয়ে আর আলাপ করব না আনলেস ইউ রিয়েলি গিভ মি সাম স্পেসিফিক প্রবলেমস, দোজ আর ওয়ার্থি অফ ডিসকাশন। নেক্সট ক্লাসে আমি অবশ্যই পেপার 2 ডিসকাস করা শুরু করব। আর পেপার 2 ডিসকাস করা শেষ হলে we're gonna schedule a class test and also gonna go for some next chapter discussion. আচ্ছা এই কোশ্চেনটা একটু দেখি। The diagram shows the square wave trace on the screen of a cathode oscilloscope. A grid of 1 centimeter squares cover the screen. The time-based setting is 10 milliseconds per centimeter. What is the approximate frequency of the square wave? Now this square wave might prove to be difficult to observe because it is not perfectly aligned with all the vertical lines. How do you observe such a graph? Now, important bit is that you need to observe similar part of the graph that is convenient for you to observe. What do I mean by this? Have a look at this graph, and similar points on this graph can be located like this. Either I can say, if you start your observation from this point, then this much, this is your first full cycle. This is your second cycle. So one cycle, 1 time period, 2 time period, 3 time period, 4 time period, like that. If you want to judge with one of the bottom corner, maybe let's say if you want to start counting from here, then maybe we use blue. Then if you start from here, then this is 0. So 1 full cycle, 2 full cycle, 3 full cycle, like that. You have to choose similar point on your whole graph, irrespective of the shape of the graph. This is a square wave, to be able to choose appropriate time periods. Now can you conveniently count how many time periods are there? There is another thing. What you have to see that in this case, the horizontal gaps represents time. Each cycle has 2 horizontal time instances. One is on the lower side and others on the top side. তার মানে হচ্ছে, I can say, let's say within this graph, this much part is a repeatable part of the graph, because if you copy paste this thing, this shape over and over, you're going to come up with this graph. You have to understand, I'm saying this is the what can I say, repeatable part of the graph. What does it mean? If I only draw this much, let's say if I say this is the repeatable part of the graph, are you going to come up with this line, this curve? আমি যদি এই জিনিসটাকে কপি পেস্ট করে পরপর বসাতে থাকি, তাহলে কি আমার এই পুরো গ্রাফটা আসবে?
না,
No, sir.
কি মিসিং থাকবে?
ভার্টিক্যাল লাইনটা,
একটা ভার্টিক্যাল লাইন মিসিং থাকবে। বিউটিফুল। Then again, if I consider that this much is my repeatable graph, আমি কি এই গ্রাফটা পাবো?
No, sir.
It's only gonna have vertical building like shape one after another. So if you observe over here, you have 2 time instances. One is on the bottom, one is on the top. So these 2 time instances make 1 full cycle. To be able to observe the graph, you need to have a good alignment observation. Good alignment observation kirokom? Have a look. This graph is starting from here, and it is perfectly aligned. One of the vertical lines is perfectly aligned on the very last line. No other line is perfectly aligned with the grid. গ্রিডের সাথে আর অন্য কোনো গ্রাফের ভার্টিক্যাল লাইন অ্যালাইন করে না, তার মানে হচ্ছে আমাদের পুরোটাই গুনতে হবে। So if we start a count, have a look. Let's count how many full cycles do we get. So I'm going to start counting from here. So these are going to be my preferable point. Let me use green. So 0, 1 cycle, 2 cycle, 3 cycle, 4 cycle, 5 cycle, 6 cycle, 7 cycle, 8 cycle. How about this much? How much of a cycle should this be?
0.5.
0.5. So altogether, the amount of cycle that we have over here, this is 8.5 time period, represented over how much time? The question says the time-based setting is 10 millisecond per centimeter. So each of the gap over here is 1 centimeter. So you count 1, 2, 3, 4, 5, 6, which means 60 millisecond. This much equals to 60 millisecond. তো এখান থেকে time period by করবা, time period by করার পর frequency by করবা। করে দেখা কত আসে? Help yourself.
Sir, 140 at 133.33 আসে sir.
Oh, sir, 8.5 কি বলে স্যার?
We did the count.
স্যার 9 আসার কথা না স্যার?
না, 9 আসার কথা না, কারণ হচ্ছে 8 এর পরে আমাদের half of a time period আছে, full 1 time period নাই. That's what I've been telling you, that the whole time period is made up with 2 parts, one on the bottom, one on the top. এটা হচ্ছে আমার 8 count starting from 0. এরপর আছে এইটুক, এটুকে তো 9 ধরতে পারবো না, এটুকে কত ধরছি? হাফ ধরছি। বুঝছো?
Yes sir, thank you sir.
Sure, no problem. 8.5 divided by bracket 60.
31.
মিলিসেকেন্ড থেকে সেকেন্ডে কনভার্ট করে নিব।
Definitely. তুমি ডিরেক্টলি ক্যালকুলেটর ইনটু 10 এর -3 বসাতে পারো, তাহলে ঝামেলা কমে যায়। আমি তাই করছি। So I'm getting 141.7. So in 2SF that would be 140 hertz. Works. বুঝে গেছে?
স্যার
জি, স্যার।
আর কোশ্চেন ছিল স্যার, পুরাটাকে আমরা কেন একটা ওয়েভ ধরি নাই?
বুঝি নাই পুরোটাকে
স্যার লাইক ওই যে শুরু থেকে লাইক স্টার্টিং ওই ড্যাশটা, তারপর রেক্ট্যাঙ্গেলটা, তারপর আর একটা ড্যাশটা, ওই পুরাটাকে কেন আমরা একটা ওয়েভ ফ্রন্ট ওয়েভ ধরে নেই?
মানে এইটুকুকে
জি স্যার, ওইটা জি স্যার।
Okay, well, if you copy paste this whole thing, are you gonna come up with this graph? Let's say this is your this is your unit mark. So you have this. Maybe I draw the next one with the red. So you have that. Maybe another green. You have that. So do you get the same graph that you have? Because the original graph is supposed to have the lower part and the top part of equal horizontal length. But do you have equal horizontal length?
জি স্যার, বুঝছি স্যার। ইয়েটা রিপিট করা যায় না ওই পার্টটাতে, লাস্টের
Exactly. I was trying to,
পয়েন্টটাতে।
beautiful. I was trying to give you the idea of repeatability so that you can actually find out that how much should you consider to be one full cycle. কারণ আমরা টিপিক্যালি তো সাইন কার্ভ পড়ে আসছি, সাইন কার্ভে তো খুব ইজিলি দেখা যায় যে এটুকু হচ্ছে 1 সাইকেল, কারণ এটুকু কপি পেস্ট করলে আমাদের পুরো গ্রাফটা হয়ে যায়। বাট দ্যাট ইজ দিস ইজ সামহট নিউ ফর ইউ, দ্যাটস ওয়াই। ওকে, আজকে এইটুকু পর্যন্ত থাক। ইটস 9:33। সো ফর দোজ হু হ্যাভ আদার ক্লাস টু অ্যাটেন্ড টু, আই উইল লেট ইউ গো। আর হচ্ছে আমি লেকচারটা উপর আপলোড করে দিচ্ছি। তোমাদের সাথে আমার টুইসডেতে ক্লাস আছে সেম টাইমে 7:30 থেকে 9:30। আই উইল ট্রাই টু বি অন টাইম অ্যাজ আই রিয়েলি আই এম লুকিং ফরওয়ার্ড টু বি অন টাইম। আর হচ্ছে টুইসডেতে আমরা পেপার 2টা সলভ করব। সো প্লিজ পেপার 2 প্রবলেম সর্ট আউট করে রাখবা। কারো কোনো সমস্যা থাকলে উইল গোনা টক অ্যাবাউট দোজ থিংস ইন দ্য নেক্সট ক্লাস। থ্যাংক ইউ ভেরি মাচ। চ্যাট উইন্ডোতে কে জানে কি লিখছে? আচ্ছা, দেয়ার ওয়াজ অ্যান আনসার। নাথিং। আসসালামু আলাইকুম।
ওয়ালাইকুম আসসালাম।
আসসালামু
Cannot end this meeting.